let's plug in sine. So we're going to take our guess and plug it in. The q of t, now we're not just going to do sine. So I'm sure that was really bothering some people the way I wrote it. We want to write sine real general and with lots of constants so we can actually have it be a physics problem with units that work out. So we need an amplitude in front of the sine, a sine, and then we need something in front of time. We need a frequency. I'm going to call that omega t because we all know where this is headed. And we also, if it's a sinusoid, it's good to throw in a phase. I'll call phi. So our guess, our better constructed guess, would be a sine omega t plus phi. So now, to plug it in, we literally just plug it into the differential equation. We need dq dt, and the derivative of sine is cosine. You pull out an omega, so it's a omega cosine omega t plus phi. And you need the second derivative. The derivative of cosine is negative sine minus a sine, and you pull out another omega, omega squared sine omega t plus phi. So now we're ready to plug in. So d2q dt2 was one of our equations, so that's minus a omega squared sine omega t plus phi equals minus 1 over LC times q, which is just a sine omega t plus phi. So basically, if this guess is correct, that has to be true. Okay? Well, you can see stuff cancels out. The sine cancels out. That's nice. This amplitude cancels out. The two negatives go away, become positive. And what this is telling you, the equation is talking to you. It's saying, you say, is this a good solution? The equation says yes, if omega squared is 1 over LC. And you could ask the equation, what about a and phi? A and phi can take any value. So the equation doesn't care about a and phi, the amplitude and the phase. The equation only cares about what omega is. So good solution if omega is, we take the square root of 1 over LC. All right, so that works. Let's try another one.